So first of all, let me thank Prashant and his team for inviting me and organizing this conference. My talk is about quantum computing. The title is an ion-atom hybrid quantum computing platform. So this is the occasion of the International Year of Quantum Science and Technology. And I must thank also the Institute Shiksha Anusandhan for sponsoring this program. So as you know that I am at the School of Physical Sciences, Indian Association for the Cultivation of Science. The purpose of my talk is to propose an atom-ion or ion-atom hybrid quantum computing platform and to demonstrate quantum gates, in particular two-qubit quantum gates. So the first question is why ion-atom hybrid system? So we know that among various quantum systems for quantum computing and quantum simulations, the most suitable systems are one is ion trap, another is neutral atom in optical tweezer arrays. So when we say neutral atoms, actually their Rydberg states are used for quantum computing and quantum simulation. Actually, neutral atoms as qubits, they are in the ground state qubits. Normally, it is considered, but one can consider also the Rydberg state as one of the qubit states. I would come to these topics. I would tell you in detail. And the third one is superconducting circuit QET. So as we know that both ion traps and optical tweezer arrays satisfy most of the criteria for quantum computing, but they have some few drawbacks. So the question arises, is it possible to build a hybrid ion-atom system for quantum computing, combining the best features of both the systems? So to answer to this question, we are proposing a model system. So we are considering a three-qubit model system, one ion in the Paul trapped, and we consider two neutral atoms, A1, A2. They are placed in the vicinity of the ion, but not very close vicinity to avoid any direct collision. So typical separations we are considering is about few microns. So summary of the main results. So in particular, we demonstrate universal two-qubit controlled JET or controlled NOT gate. Both are universal gates. If one can demonstrate either of them, then the other will follow automatically. You can combine two-qubit and single qubit gates to make all possible superpositions of the two qubit states which are called entangled states. So what we show is the CJET or CNOT gate operation in the hybrid platform. We propose two different protocols to implement ion-atom and atom-atom control JET gates with more than 90% fidelity. So since we are considering a hybrid system, so we need to consider ion-atom quantum gate, two-qubit quantum gates, as well as atom-atom quantum gates. So we demonstrate both the gates in this talk. So in particular, we show CJET gate between two atomic qubits as large separation, larger than 20 micron, by utilizing ion-mediated interaction-induced Rydberg blockade. So what is this ion-mediated interaction between the atoms? I'll come to this point. So here is my plan of the talk. So I would first discuss some basics about quantum computing. Then I will give an overview on ion trap and Rydberg atom quantum gates. Then I will discuss our proposed hybrid system. In particular, I will show atom-ion CNOT gate using phonon blockade. So this is a phonon blockade term we are introducing for the first time here. So this is our very recent work. A few days back, we obtained some results, and these are unpublished. And atom-ion atom Toffoli gate using phonon blockade. This part is also unpublished. Again, we use phonon blockade. And then we show atom-atom control dead gate with ion-mediated interaction. So this is published last year in PRA. So about then I would discuss our main results and discussions. So about some basics on quantum computing. So all of you are familiar with qubit. What is qubit? A density matrix formalism and the Bloch sphere. But for the sake of completeness, I would briefly introduce these concepts. Then I would describe 1 and 2 qubit quantum gate operations, universal set of quantum gates. So about qubit, so any two-state system can be considered as a qubit. And then any two-state system is a pseudo spin-half system. So one can apply Pauli spin algebra. So for example, here we are considering single qubit 0 and 1. It could be some energy eigenstates of an atom. It could be a spin-half, any spin-half system like electron, or any two-qubit system or two-state system. So 0, one can represent as a column vector 1, 0. So if it is populated, then this 1 is it is in the upper entry is 1. Otherwise, it is 0. So and one can then consider superposition of any of these two states. Then it could be an A and B, any arbitrary complex numbers. So about 1 and 2 qubit quantum gate operation, it is basically manipulation of any arbitrary superposition of 1 or 2 qubit states. When we say 1 qubit states, then it is local. Of course, it is 1 qubit. When you say 2 qubits, then 2 qubits can be delocalized. They can be separated by a long distance. Still, their state is inseparable quantum state. It is called then entanglement. So what about what are the good qubits? So those qubits are called good qubits, which have very long lifetime of the superposition between the qubit states. And so this lifetime must be much longer than the gate operation time. So when you do any gate operation, you apply some laser pulses and you do some operations. Meaning that you accomplish the unitary operations. Okay? So that requires some time. So the lifetime must be that gate operation time. So that means that the gate operation time should be much faster than the compared to the lifetime of the superposition state. So for any atomic or ionic qubits, gate operation is usually performed by applying laser pulses on the system. The Hamiltonian of laser qubit interaction is a general Hamiltonian one can write in this form, where this delta is the detuning between the laser and the qubit transition frequency. So this is the qubit transition frequency, the energy difference between the state 1 and 0 divided by Planck's constant is the transition frequency. And the laser will interact strongly when this detuning is small compared to other energy scales. So that then omega is called the Rabi frequency, which is basically the In case of atomic qubits or ionic qubits, it could be electric dipole coupling or magnetic dipole coupling. And phi is a ladder phase. So this is, I have missed here H cross, or you can consider this H cross equal to 1. And then you have the Pauli algebra. One is the identity operator sigma z, sigma y. So this, just to recall all these features, and okay. Then what about single qubit gate? It is basically the evolution of the state under the action of this unitary operator ut. So if you consider this t, the time, so you allow the system to evolve given an initial state. So then in order to do single qubit gate operation, the important first thing to do is to prepare the system in a particular initial state I. And then you have to create some pulses, some designer pulses, so that it acts only at a certain time t. And then you design your Hamiltonian in such a way that after the evolution for the duration of time capital T, it gives you the desired state. You want to prepare a desired state. So this is called a single qubit state. So since it is all about Pauli spin algebra, and one can express in analytical form the evolved state. So this is the initial state, this is the final state. So these are, so you can parameterize with these parameters theta, delta, beta, where this beta is actually the effective coupling. If delta equal to 0, then this is just the Rabi frequency, and there is a half factor also in the Hamiltonian. So this theta will be then half of this quantity. So half appears because it is spin half system. And then so if beta t is some number nu times pi, then it is called the pi nu pi pulse. If nu is equal to 1, then it is pi pulse. It is half pi pulse. So then one has to make these kind of pulses in order to do quantum single qubit quantum gate operations. So these all are tuning parameters. The beta you have handled to control this this beta, because this is omega, this Rabi frequency is proportional to the intensity, and delta the ledger frequency. So you can make desired gate single qubit gate operation, provided the lifetime and the spontaneous emission or lifetime of the states are quite small. Okay. So and what about two qubit gate? Then you generalize this Pauli algebra for a single qubit, for multi-qubit, in case here it is 2 qubit. Then you do outer product, and you have then 4 basis states. So in 2 qubit gate operation, the first qubit is called the control gate, and the second one is called target. Any question? So what about universal 2 qubit gate? So there are 2 universal 2 qubit gates. One is called control Z, another is called control naught, and these two are equivalent. This means that if you can make either of them, you can easily then make other one, just by combining the former gate with some single qubit gate operations. So CZ gate means if initially the state is in the lower state 0 0, then it remains 0 0. If 0 1, if it is 1 0 1 0, if it is 1 1, so depending on this control, if control is in state 1, then it occurs a -1 sign. So this is called control Z gate. And there is C naught gate. C naught gate again 0 0 remains 0 0 0 1 0 1 1 0. then it becomes 1 1. So it flips. If it is the control is state 1, then it will flip the other state. 0 will become 1 and 1 will become 0. So this is called control NOT gate. So and in terms of matrices, you can express this control NOT gate in this way, and this is the operator for control NOT gate. So now I give an overview on ion and Rydberg atom quantum computing. So if you have a single qubit gates and universal two-qubit gates at your disposal, then in principle you can build a quantum computer. You can do most of the operations in principle. Okay, so this ion trap quantum computing uses trapped ions, and they serve as excellent qubits because you can trap ions for several hours. If not days. Okay, so and coherence time is of the order of millisecond to second order. So that is the decoherence time is quite small, and the coherence time is quite large. Okay, so and these are individually addressable with lasers because a typical separation between the ions in an array of ions is of the order of 5 micron. And typical for a good laser, the beam waist or the size of the beam is typically a few microns, so one can easily address single ions with lasers. And Coulomb interaction, along with harmonic motion of the ions, give rise to what is called phonon collective modes, and that can be utilized for two-qubit gate operation. On one hand, phonons are useful for doing quantum gate operations in ion trap quantum computing. On the other hand, it creates some hindrance also. Because if you want to scale up the system by adding more and more ions, then number of phonon modes becomes quite large, and it becomes then messy. So, and again, you cannot control Coulomb interaction because this is always there because these are ions. So, but in case of atoms, as we will see that, you can switch on and switch off interactions between the atoms, which is not possible in case of ions. So ion trap has all the good features as a reliable quantum architecture for quantum computing, except perhaps scaling. So scaling is a problem, but people are working to scale up by inventing some innovative ways. Okay, by reconfiguring the atomic the arrangement, so that is a possibility. So for quantum dynamics of trapped ions, one can see these are very good review articles. One is by Wineland, so, and another is again by Wineland group. So these are one can look at. So about Rydberg atom quantum computing platforms, so this is the development of the last 2 decades. So Rydberg atoms in an array of optical tweezers have emerged as a good quantum computing platform. Okay, so because that the lifetime of Rydberg state, if you excite the atom to a very highly excited state with large principal quantum numbers, n is, if n is of the order of 100, then lifetime of the Rydberg state is typically of the order of 100 microseconds. At 0 temperature. Okay, and it has a very good scaling properties. For example, the orbit size of the Rydberg goes as n to the power 2. In binding energy, you know that Rydberg formula, this is 1 by n squares, but there is a quantum defect term also. So this goes as n to the power minus 2, and radiative lifetime goes as n to the power 3, and polarizability scales with that. So this property, polarizability, we will use in our gate operation. So it goes n to the power 7. So there is a huge, giant enhancement of polarizability if you excite an atom to Rydberg state. And dipole matrix element goes as n squared. So for a review on quantum computing with Rydberg atoms, one can see this reference of Walker and others, reviews of modern physics. And what property one uses usually to perform gate operation using Rydberg atoms? So typically these Rydberg atoms interact very strongly because of the enhancement of polarizability, and this so because two neutral atoms interact through their polarization. Okay, so then so that's why they interact very strongly even if they are separated by a few microns, say 3, 4, or 5 microns. So this leads to what is called Rydberg blockade, and that can be used for two-qubit gate operation. The Rydberg quantum computing system can be scaled up easily because you can excite, de-excite the atoms to Rydberg atoms. So that means you can, at your will, you can switch on or switch off the interaction between the atoms. So neutral atoms in ground state can be trapped for a time of the order of second. In case of ions, you can trap them for many hours or days. So these are some contrasting aspects between the Rydberg atom quantum computing platform and the ion trap quantum computing platform. So these Rydberg atoms have many good features, but individual addressing is difficult for two-qubit gate operation, because in order to have a Rydberg blockade, you have to bring the two Rydberg atoms in the vicinity of a few microns. So that creates a problem for individual addressing. And three most prominent quantum computing platforms as emerged over the years. One is superconducting circuit QET, another is ion trap, and the third one is Rydberg atoms. So I will not go into details of this. You can find many review articles and many developments. So here we propose an ion atom CNOT gate using what we call it phonon blockade. So here we are considering a ion, beryllium plus, and it is trapped inside a ball trap. And at a distance, we place a neutral atom, Rydberg atom, trapped in an optical tweezer, and the typical separation could be 4 micron or so. And then we use this Rydberg state of the rubidium atom with n equal to 120 as an auxiliary state. So we'll make use of this Rydberg state to perform the gate operation. So the idea is the following, that when we excite the Rydberg the atom from state 0 to state R, so we apply a laser that couples the lower state of the qubit, of the atomic qubit, to the Rydberg state. And the ionic qubit 0-1 is coupled through a 2-photon transition, or it could be a single photon transition as a model. So we are considering, say, 0 as some hyperfine state of beryllium and in the ground state, and this could be a D state, long-lived metastable state. And then in the ion case, ion is trapped inside an harmonic oscillator. So it has a harmonic oscillation frequency. So these are we called phonon. So in this case, it is only one ion. So these are actually local phonon. And by 2-photon process, one can selectively excite phonons. Suppose the ion is trapped in the Lamb decay regime, and it is prepared in this in a particular phonon phonon or harmonic oscillator states, the ground state or the first excited state of the harmonic oscillators, so 0, 1. So we use this one electronic internal state as the one of the qubit state, and another state, internal state, as another qubit state. And we also combine these states with the phonon states. So actually 0 and 1 phonon could be one state, and 1 and 0 phonon. So this is the picture we have in mind. And in this case, when we apply this laser field and we apply a pi pulse, then we excite this to this Rydberg state. So when this is in the Rydberg state, this Rydberg state will interact the ion very strongly by ion atom interaction, and that goes as n to the power 7. It is proportional to polarizability. So there is a huge enhancement of the interaction between them. So as a result, there is an interaction-induced shift in the ionic state. And here we are plotting this shift. Suppose in the absence of interaction, when atom is in the ground state, then the harmonic oscillation frequency is 11.2 megahertz. So when we excite, then up to the harmonic approximation, because we expand the interaction between these two states up to the second order in distance, then we get new harmonic frequency, and that is shift. So it goes from 11 to 9.5 at a distance of 3.5 micrometer. And the equilibrium position also shifts. So that leads to what is we call phonon blockade. Because if it is in the absence of this ion atom interaction, so an atom is in the ground state, then practically there is no interaction between the ion and atom. So when atom is excited to the Rydberg state, then the interaction is switched on. So when the atom remaining in the Rydberg state, we have a strong interaction-induced phononic shift, and that will prevent the ion to excite to the state 1. If it is in 0, it will not go to 1. If it is 1, it will not go to 0. So this is the property. This is the property we are using here to accomplish CNOT gate, because if it is in the 0 atom, then there is no change in the ionic state. But when it is in 1, then there is no interaction between the interaction-induced shift. There is no phonon blockade. Then there is the change of the state. So this is the idea we are using here. And so next we demonstrate this that numerically prove that it works actually. So what we are considering as qubit state for the atom is atom in 0 state, and this atom is in 0, and ion is the lower state. We are calling it a G state, ground state or excited state, and one phonon also. So G tilde G means the ion is in the ground state with one phonon. So then we plot here the amplitudes of the states. So this red dotted curve, actually the amplitude of the atom remaining in 0 and G. So this shows that, and so we are plotting here the real part of the amplitude and the imaginary part of the amplitude. And finally, we get actually what we want, we proposed, that it works actually. So here we are showing those evidences that it actually works. So actually, so we have checked all those states, and then we also calculated the fidelity of the states. and we have found the fidelity is about 92%. And so this is how it works. Actually, if atom is in 0 state and the ion is in the lower state, ground state with one phonon, then after the pulse sequence, what we get that it remains in the 0. If it is 0E, it will remain in the 0E. But when it is 1, then it will flip with a minus I sign. And if it is E, then it will go to G. But minus I, that is a phase that one can manage with by applying another single qubit gate operation. So it works actually. So single qubit gate operation. So we can have a single qubit phase gate, pi gate, and we get atom ion C0 gate. So finally we get this kind of. So in order to get rid of this I sign, then we apply a single qubit phase gate, pi phase gate on the atomic qubit. Then this minus I will become minus I into I, so it will 1. So finally we get this. So we have calculated fidelity. Fidelity comes out to be 92%. So now we consider atom ion Toffoli gate. So Toffoli gate is a 3-qubit gate where 2 qubits are used as the control qubits, and the third one is used as the target one. So here we are considering the both 2 atoms, 2 rubidium atoms as control qubits, and the ion as the target qubit. So we have a linear arrangement, and if both atoms are in the lower qubit state, that is 0 state, or either of them in the 0 state, then we have strong interactions between the atom and Rydberg state, atom in the Rydberg state and the ion, that prevents the state flip in the ion. So if it is in the 0, it will remain in the 0. If it is 1, it will remain in the 0 because of this strong phononic shift. So the frequency of the phonon will be shifted. That will actually block the excitation in the ion. So it works either of them if it is in the 0. So there will be flip in the ionic state only when both atoms are in the state 1. So that means it is a direct demonstration of the Toffoli gate. So in order to demonstrate this numerically, we have considered these parameters. The atomic Rabi frequency is 2 gigahertz and ionic Rabi frequency 0.2 megahertz. And phonon frequency of the ion that we were considering the beryllium ion, it is 11.4 megahertz. And on the shift in the phonon frequency, thus the shifted phonon frequency when atom in the ground state, either of them is typical 10.56 megahertz. So this shift is 0.84 megahertz. So here we are showing the evolution of the amplitudes during the pulses. So the pulse sequence are like this. We first apply a pi pulse on atom 1, and then we apply the second pi pulse on atom 2, and then we apply the pulse on the ion, the qubit. And after that, we apply another pi pulse to bring down this the atomic qubit from Rydberg state to the original qubit state, another pi pulse. And finally, on the atom 1, we apply another pi pulse. So here we are showing the real part of the amplitude and the imaginary part of the amplitude. So we are considering this both atomic qubits as control qubits. Both are in 0 states, and the ion is G and with one phonon, then we are considering this kind of transitions via this Rydberg state. So if it is in the 0 state, and then we are applying a laser pulse to couple this 0 state to the Rydberg state, then this first atom will be excited to Rydberg state. And so we are plotting here the real part of this state and the imaginary part of this state finally. So then it shows that actually this is the first pi pulse and this is the last pi pulse. So this representation is not very appropriate, but you have to think of this is the first pi pulse, this, sorry, and this is the last pi pulse. So what happens that after all these pulses on the atom 1, it goes to this state. 0, 0, it remains in the G1. You can see that this is the real part, and this is the, so through this Rydberg state it goes to that. So similarly, we have shown that if either of the control qubits in 0 and the other one is 1, then also we get the similar transition. So it will remain in the same state. But if both are in state 1, then there is a flip. If it is 0 G, then it will go to E, and if it is E, it will go to G. So this is how we demonstrate both 2-qubit and 3-qubit gate operations in this hybrid system. Now we consider atom-atom control jet gate using ion-mediated interaction. So as a model system, again, this the same model system in linear configuration. We have a ion and then 2 neutral atom qubits, and the separation between the ion and the atom is 11.5 micron. So between the 2 atoms, the separation is 21 micron. So these are good, these properties of the ionic trap, and we have already discussed. And so we know that how to represent the qubit states. And so we consider the Rydberg state with a principal quantum number about 100. And we consider in this case to demonstrate atom-atom control jet gate, we use the charge property of the ions only. We don't use ion as a qubit because we are interested only 2 atomic qubits. So ion can remain in any internal state. Suppose G is the internal state, it is a ground state, it is in the ground state. Because this ion atom interaction does not depend on the ionic internal state. It depends only the charge state of the ion. But in contrast, the atom-ion interaction actually depends on atomic internal states, very Rydberg states. So it does not matter whether ion is 0 state or 1 state or any internal state. So because this charge will polarize the atom, and then the polarized atom will interact with the ion. So it is actually it goes as 1 by r square, because polarization depends on the electric field, which is 1 by r square. And then this polarized induced dipole moment will interact with the atom itself. So it makes 1 by, so this C4 goes as n to the power 7. So there is a huge enhancement in the polarizability, which leads to a strong interaction even at separation of 11 micron. So here is our protocol that we consider this. So here we are considering that control atom and target atom, and in between them there is an ion, so we are not showing this. So ion is passive, but it just gives you the charge property to have the ion mediated interaction between the two atoms. So what are the important points to keep in mind? That ion mediated interaction is strong enough even at separation of more than 20 micron to cause Rydberg blockade. So this is similar to the phonon-mediated interaction between two electrons. We are familiar with the superconductivity, the standard superconductivity. It occurs due to the attractive interaction between the two electrons due to phonon-mediated interaction. Now here we are considering the ion-mediated interaction, because one atom interacts with the ion strongly and another atom interacts with the strongly. And if we eliminate the ionic degrees of freedom, then we will end up with an effective atom-atom interaction mediated by ion. So we are using this property, and now we consider control Z gate. So here we are demonstrating that if it is both atoms are 0, 0, then nothing will happen. If it is 0, so here unlike ion atom control, ion atom gate, in this case we are applying the laser pulse on the state 1, the upper state. So we are coupling this state to the Rydberg state. So if it is 0, 0 and 0, 1 and 1, 0, so when we apply the first control atom, so first pi pulse on the control atom, then when it is in 1, it will go to Rydberg state. And if we apply the target, so this is target atom, when we apply the target atom at 2 pi pulse, and again in control atom we apply pi pulse. So finally what we get after these operations, the 0, 0 will remain 0, 0, 0, 1 will go, acquire a -1 sign, 1, 0 will acquire a -1 sign, and another, this will acquire a phase minus e to the power I theta, where theta depends on the ion atom interaction. And if we consider this theta to be pi, then it is 1 minus e to the power I theta would be 1. So it is a control Z gate. And if we have a control Z gate, then combining with single qubit gate, one can easily make control NOT gate. So here is some mathematics that how we do it. So we have this J stands for atom number, or atom 1 or atom 2. And this is actually C to the power 4 divided by the distance between those. We are considering a one-dimensional model for the sake of simplicity. And so ion is in the internal state G, and the atom, when atom is in the Rydberg state, then we have this interaction. So this typically this extension of the ionic motion is about 30 nanometer or so. It is much less than 1 micron actually, and the atomic in the trap, it is it could be 1 micron or more than 1 micron. So this we are not considering the motion of the atoms, but we are considering the motion of the atom of the ion quantum mechanically as phonon states. So then, since the distance is typically 11 micron, so compared to 11 micron, if it is 30 nanometer or 50 nanometer, it is quite small. So we use this Zi by Zj as a small parameter. And then we expand this, and this Zi is used as a quantum mechanical expression for the position operator in terms of phonon operators. So we retain the first order term, and then what we do is that we expand this the evolution operator, considering this quantity, this Zi by Zj is a small parameter. Okay, so what we do, it is called the Magnus expansion. So in the evolution operator, we have two kinds of operators, atomic operators and phonon operators. Now, then if we expand up to the second order, then we can define an effective Hamiltonian, and that effective Hamiltonian is, we write it H equal to H2 up to the second order. So we have then this, one can write it in this form, that there are two phase factors. One will be first order and another will be the second order. So retaining the terms up to the second order, we obtain an effective Hamiltonian that contains an ion-mediated interaction term. So this is how we eliminate the ionic degrees of freedom. Ionic degrees of freedom here is the phonon. So when we apply, then we get an effective Hamiltonian. So for details, one can see our paper published in PRA last year. And so what again we show the pulse sequences. So we have any question? Okay. So we have we are using this kind of pulse sequence. First pi pulse on the first control atom, and the twice pi pulse on the target atom, and then again pi pulse on the first atom, the control atom. So when this control atom in state 1 and coupled to Rydberg state by a laser, then this the target atom, suppose in state 0 or 1. So, and there is no so only we are addressing only the first atom, not the target atom. Then the evolution will be governed by this first atom, the Hamiltonian corresponding to laser Hamiltonian, laser atom interaction, and the interaction Hamiltonian. Okay. So when the control atom is in R, so we then excite this pi pulse will excite the atom to Rydberg state, and it will remain in the Rydberg state because it is long-lived state. And then pulse is switched off because it is a pi pulse. So after that, it is in the. So then now we apply this two pi pulse on the target atom. Then what is the state of the control atom? It is in state R. So when we apply this pi pulse, then there will be Rydberg interaction, strong interaction. And that will prevent both the atoms to be excited simultaneously to the Rydberg state. This is called Rydberg blockade. So either of them will be in the Rydberg state. So that means when it is in the Rydberg state, then because of the strong interaction, ion-mediated strong interaction, even though we switch on this laser, the state will not go to the Rydberg state. Okay, so this property we are utilizing for the gate operation. So then we have this kind of Hamiltonian, and this two pi pulse is on. We have that's the second atom laser interaction. Then this interaction and that interaction ion, and then we have ion-mediated interaction between the Rydberg state. And when the control atom is in Rydberg state, is acted upon by a laser, the third pulse, then it will just take this atom from Rydberg state to the one state. It will bring back. So So this is how, and then we show the numerical evidence that it works, and we again plot different amplitudes and for all the pulse sequences. So what finally we show that it works. Okay, that if we have so if we have 1-1 state, and the phonon and the blue curve shows that it is 1-1, and the phonon state is 0 or 1. So we consider initially the phonon is either in 0 state or 1 state, and so one can prepare that by cooling the ion, and then we calculate the fidelity of the gate. And in order to calculate fidelity, we are utilizing this formula given by Pedersen, Molmar, and Molbar in Physics Letters 2007. And utilizing this formula, we have calculated the fidelity at 97%. So only source of error we considered is the spontaneous emission from the Rydberg state. And then we plot the phonon distribution after each pulses. So if we have the first pi pulse, and if we prepare the phonon in 0 state, after pi pulse, we have this kind of distribution. And after applying twice pi pulse on the target atom, the second atom, so that means T is 3 pi by 2 omega, then we have this kind of distribution, because in this case, one atom is already in the Rydberg state, and another atom is coupled to the Rydberg state. And then we have finally, when we apply the last pulse on the control atom, then we have this kind of phonon distribution. This is if we prepare the phonon in 0 state. If we prepare the phonon initially in the 1 state, then we have this kind of distribution. So what does it show? It shows that the phonon distribution contains a signature of the atomic states. So by detecting phonon distribution, one can predict or tell about the quantum states of the atom. So to conclude, so I have 5 minutes left. So our group members who contributed to this work are this is Subra's work, the published one, and now she's writing another paper to propose ion atom quantum gate and 3-qubit Toffoli gate. And Shubhanko already obtained PhD, and he is in Ahmedabad working with Bijay Shahu as a postdoc. And he is a second year PhD student, and Onshi also obtained her PhD already. And to conclude then, so in conclusion, we have demonstrated C0 and Toffoli gate operation with more than 90% fidelity between an ionic and a neutral atomic qubit by making use of the what we call phonon blockade. So this current term we are using, or we are introducing for the first time, that is interaction-induced phonon blockade. We have demonstrated CZ gate operation with 97% fidelity between two distant atomic qubits by making use of the ion-mediated interaction-induced Rydberg blockade. The ionic phonon distribution can be measured or for information about the atomic qubit states. So it indicates that by looking at the phonon distribution, one may infer information about the atomic qubit states. And probably this is the first proposal for an ion atom hybrid quantum computing model. Thank you very much for your patience. So with this, I conclude here.
Thank you, sir. Any question from the audience?
So, Bimalendu,
Yes, sir. Prashant, sir.
what is the status now? I mean, for example, neutral atom, ion is functional. How about neutral atom ion together? Are there any machine building going on?
Some experimentalists are exploring the collision dynamics mostly. Our Netherlands group, they are trying. So they have published some theoretical ideas about ion, but experimentally I have not seen any work on hybrid system.
But this blockade has been demonstrated concretely, isn't it?
Yes. With Rydberg atoms, so people have demonstrated quantum gates using Rydberg blockade.
Similarly, Rydberg atom itself, has it been used for something like sensing or some other kind of work?
Yes, people are considering that for quantum sensing purpose, because Rydberg state is very sensitive to electric field.
It's very nice. Really enjoyed it. Thanks.
Yeah.
Okay, if no more question, we can thank sir for such a wonderful talk. Thank you, sir.
Thank you very much.
You can